Last lecture, we talk about the transverse field Ising chain with random couplings and random fields. And we develop a procedure or a scheme, a simplified scheme to try to solve this problem. This scheme is called strong disorder normalization group, and it does the following. It searches in the chain, throughout the chain, the strongest coupling, let's say a field, and assume that all the other energy scales are much smaller. So you can do perturbation theory, meaning that at zero order, this spin is aligned to the local field. So it's static there, doesn't move. And therefore, it can be removed out of the game because it now is a static degree of freedom. We know its state. And then do perturbation theory to compute how the neighboring spins interact. If the energy scale is a coupling constant, these two spins will be always aligned. So actually, 2 degrees of freedom are essentially 1. So we get these 2 spins, fuse them in a new one, which has a new magnetic moment. And is under the influence of an effective field. And this effective field has the same structure as the effective coupling. So this is due to duality between exchange J and H, a paramagnetic state, when H is very strong, there is a state in the ferromagnetic side, when J is strong, that you can correspond these 2 states. There is one-to-one correspondence between all states in the ferromagnetic side and the paramagnetic side. This is due to duality, and this is reflecting this decimation procedure here. We wrote down flow equations for the distribution of these couplings and fields. It's written here. There are 2 of them, integral differential equations, and there is a solution of these equations, very lengthy one, but if you know the solution, you can do an ansatz and see that this is the solution, because we know that's the solution. So as we know that this is a solution, I didn't show you that, but we can come up with ansatz, and this ansatz it makes sense a lot. Why? Because it's a singular distribution at 0. And this is what happens when you iterate this procedure. You are generating couplings that are weaker and weaker, and fields that are weaker and weaker, so this must be a distribution that is singular at J equals 0 or H equals 0. So this makes sense. You can put it back to the flow equations, and you can see what are those parameters in your ansatz. So my ansatz, well, that's the cutoff, that's the J, and these are parameters that depends on the cutoff. So that's the equations for your parameters. And out of it, we are ready to do the following. If I subtract this of that, I get that R minus P is a constant. It's a constant of the flow. Doesn't depend on omega. Right? Because if you subtract that and that, P minus R divided by omega, and this gamma is just omega. So this is d omega, omega d omega, right? D gamma. Minus with a minus sign because it's the bottom. Then we see that this is a constant of the flow. I don't need to solve the entire set of equations, but I can make sense of what is R and P, these 3 parameters. If I make the log of age average, it's just simple that, and then I get 1 over R. And the same thing for J, 1 over P. So these P and R, they are somewhat parameterizing the value, the mean value of the log of the couplings. And this is an important quantity because this structure that is multiplicative in log scale, they are additive. And we can make reasoning of this additive structure, but I'm not going into these details here. I can rewrite, since I have a P and R, and I define this constant as P and R, I find that. Simple, just substitute and you get that. So if delta is 0, means that the log of J is equal to the log of field of couplings. And this rings the bell like something analogous to T minus TC, which is the distance from criticality. Because when delta equals 0, the log of these distributions are the same, the average value. Okay, so the critical point must be delta equals 0. And if delta equals 0, means that R equal H. And if R equal H, this equation here simplifies to something very simple, minus P squared. And P and R equal 1 over gamma when gamma is infinite. Of course, there must be some integration constant, but I'm just interested in the gamma infinite limit, and that's what you get. I'm not paying attention to the constants of integration constants. So the fixed point distribution or critical distribution is this one here with P and R being 1 over gamma. It's highly singular. When gamma goes to infinite or omega goes to 0, it's very normalizable. And I did not show you that, but even if you start with something that's not this ansatz, but something different, because of this structure, you flow to this distribution. Means that this distribution does not depend on the initial distributions. This means universality, that the details of the distribution are not important. You always flow to this singular distribution. This distribution has a character which we call infinite randomness, meaning that the width of the J's divided by the mean value of J's goes to infinite when you lower the temperature or lower the energy scale. Another way to see that, you can compute the mean value of the J, which is the cutoff over gamma. So if you take omega to 0, this goes to 0 as omega. But if you take the typical value of the J, well, there is exponential of gamma here. So it's completely different behavior. So the typical value, which I define as exponential of the average of log J, is totally different from the mean value. So if you look at the gamma here and the exponential of gamma, very different. So what do we do with this result? Well, we have to make sense and use of it, right? And the key point is to realize that the distribution is very singular at the 0 energy. This means that the remaining spins are essentially free. So you start with a narrow distribution at high energy. The initial cutoff, I don't know, 1,000 kelvins, hundreds kelvins. And now you're interested in low energy, 1 Kelvin, millikelvin, or even the ground state. You keep decimating, you come to this distribution or very close to it. Once you are very close to it, once you develop the singularity, then you can face the renormalized system, the renormalized chain, as essentially a free chain, free spins, composed by free spins. But these are spins that were left over from the decimation, not the original spins. So I have to keep track how many spins are left at each energy scale. At 1,000 Kelvin, at 100 Kelvin, at tenths of Kelvin, Kelvin, millikelvin, and so on. How many spins are left when you keep doing this procedure? And this is given by this equation, which probably is one of the most important equations in this strong disorder normalization group technique. So I'm defining the density of spins as the number of remaining spins divided by L. So it is a number between 0 and 1. So when you do a decimation, meaning that you decrease the energy scale, you decrease the number of spins or the density by how much? Well, the number of spins that you removed is proportional to the number of spins available. So it's proportional to n. But whenever you have a decimation of fields or a decimation of couplings, you always remove 1. So I put 1 times the probability of having a coupling decimation, 1 times the probability of having a field decimation. That's why it's the omega here, because PD is this probability. Yeah, when I decrease the omega, I also decrease n. So negative, negative, yes. Sometimes it makes confused when you put gamma, because then you increase gamma and diminish n, because of a log of 1 over omega there. And this gives to the solution at criticality, at least, because we know how much are those guys here, right? These are n. So p omega, omega is just the small p. So this gives minus 2 gamma d gamma. If I put this n down here, I get the log, and so I get the n for gamma. I'm not taking care of integration constants. This is 1 over gamma square, which we usually say that this is 1 over gamma to minus 1 over psi, where psi is 1/2. It's called tunneling exponent. And I will make sense of why this name. But it's universal. As the fixed point is universal, all quantities that you can think of will be universal. So the exponents will be universal. This relation here is already an important relation because it gives us the relation between length and time scales. What do I mean by length and time scales? Well, this can mean many things. One, for instance, is the following. Given excitation, it has a typical time associated to it to relax. And this excitation also has a length scale associated to that. So how are the excitations? So suppose we go here. I did this decimation. I got that spin. I did another decimation, and that was more or less like this, right? So if I come back a little bit here, when I fuse these guys together, and suppose that the distribution is already very singular at this scale, I have a spin, an effective spin that has some length, and the energy associated to that length is the energy scale when it was decimated. Suppose you do this decimation here, right? So this is a two-level system which has a time scale associated to that. Which is this time scale? It's the inverse of the gap. Right? If you do the Hamiltonian exponential of omega t, omega is the energy, so the time to flip up and down is the inverse of the energy. So our omega is the inverse of time. But this spin here is not the original spin. It was already clamped many spins together. So how many spins were clamped together? More or less the distance between these two spins, because everything in the middle was clamped together, more or less. So that's the length of this excitation. If you come back to the original spins, it means that all these spins are flipping together. So this is excitation mode. It's a localized excitation mode. So n is L minus 1. And this is the length of your excitation mode, localized excitation mode. And tau is omega 2 minus 1. The time for this excitation mode to flip. So it's kind of a coherent tunneling. That's the excitation modes that we have in this problem. These many spins, they talk to each other, they are far apart, but they tunnel together. So if you do this, what we get that tau is proportional to exponential of L to psi. This is called activated dynamical scaling. And we can compare our dynamical scale with the clean system dynamical scaling. If there were no random J's and no random fields, when J equal H, there is a transition. And this transition has modes. At that point, you can insert energy to the system, it can acquire energy, and get this energy put in a mode that has some length. And this energy is the inverse of time. So in the clean case, this relation is tau L to Z, and the Z is equal 1. It's called critical dynamical exponent. But this sort of relation is not of activated type, right? Because tau relates to exponential of lengths, and here's power law. This is usually called power law dynamical scaling. So formally, Z dirt is infinite. That's the only way that I can put a power here that can compare with exponential. So this is a much slower dynamics than this one here. If you give 1 joule to your clean system, the time related to that is 1 over that in conventional units, and the length scale will be something. You do the same for the dirty system. That length scale is completely different. So that's how disorder, no matter how weak it is, change the system already. Let's see more things, what's going on. Let's compute the low temperature thermodynamics. Let's start with entropy. We have the receipt, right? The remaining spins are essentially free. So what's the entropy at a certain energy scale? Since the spins are free, each one gives me a KB, a log 2, times Ln. Because that's the number of spins, right? Ln. L, the size of the chain, times the density. So this is proportional to n. KB log 2 times L is a constant. I don't care about the constant. But n is gamma 2 minus psi. 1 over psi, yes. So if I associate now this energy scale with temperature, this means that now omega is kBT. Why kBT? Because you can run your SDRG procedure until the omega is kBT. Because when omega is kBT, you cannot neglect anymore the high excited state, because then you have a thermal energy to excite it. So you have to stop there. So omega is kBT, then gamma is log of what is there. So this is 1 over log omega I over T to power 1 over psi. So this entropy vanishes very slowly. You put T to 0, this number goes to infinite, but only logarithmically. So slow, the temperature goes very slow to 0. Very different from the clean system. Entropy in the clean system vanishes as T, much faster. I run out of space. This what? Yes, that's the critical point, right? So that's a requirement. Log of H equal log of J. See, as long. Yes. We're gonna get out of this criticality point and then see what change. Correlation length is infinite here. I didn't compute the correlation function, but it's infinite. This is critical system. It's infinite. I have to scale with what? You want it to be finite. For it to be finite, you have to get out of criticality. I didn't do that yet. I will go to that. And that this in the clean system, in the dirty system is 1 over log omega I over t to 1 plus 1 over psi. And in the clean case, this is T. So a much larger specific heat. Why is a much larger specific heat at low temperature? Because we have much more energy states, energy state at low energies. So the density of states at low energy must be higher in the dirty system. Susceptibility. So how much is that? Chi. Each remaining spin will give me a Curie contribution, right? 3 spins, they give a contribution to susceptibility as moment squared over T. So it's N times the Curie contribution, mu square over T. And I just erased here, but the mu grows when you lower the energy scale. How does it grow when you lower the energy scale? It grows as gamma to phi. I will not show it here. It's a very beautiful derivation to compute this exponent, but very lengthy. It's not. I don't have time to do it here. But phi, it's 1 plus square root of 5 divided by 2, which is the golden mean. The golden mean, why the golden mean? Because sometimes you add up and sometimes you remove. Sometimes you add up and sometimes you remove. But this system is a fractal because it's critical. So what is the ratio of things that when you cut it back, it has the same proportions? It is the golden mean. To show that properly, it's very lengthy, but it is an exercise for you guys. So how does it go? N goes as gamma to minus 1 over psi. This is gamma to 2 phi, and we have 1 over t. So this is a log. This is practically a Curie law furnished with a log. This is 1 over t, log of omega I over t, to the power 2 phi minus 1 over psi. That's the susceptibility. Magnetization, coming back to André's objection that we should have put magnetic field, a longitudinal magnetic field. So what am I doing? I'm sitting at the critical point, 0 temperature, and putting a magnetic field. So does it complicate things? Actually, no. The problem is solved already. Why? Because the spins that were decimated when and this b is small because we are just putting an infinitesimal b or a small number, and C, demagnetization. So initially, the couplings that were decimated has a much higher energy than the magnetic field energy, mu B. So if that is the case, these decimation that we are done are in energy scales much higher than mu B. So we did good. And the spins that were decimated, they are aligned to the X direction. They don't care about the B, which is in the Z direction. So these spins that were decimated give nothing to the magnetization. They are flipping up and down, Z minus Z, Z minus Z. That's it. But now you lower the energy. So when you lower the energy, when mu B equal your cutoff, and B is very small, so you did a lot, means that you are very close to the singularity already, to the fixed point. This means that you have to stop there and consider all the remaining spins as free. And because they are free, they will align to the longitudinal field. So run SDRG until omega is mu B. And you have to put the average mu value of B, which gives a log. This is omega, this is log of omega, which is actually B at first approximation. So this means that the magnetization is what? Well, each spin that are left will align with the longitudinal field and give the magnetization. So it's proportional to the density. And each spins give a magnetic moment for the magnetization, mu. So this is gamma to minus 1 over psi, gamma to phi. And this gives us log omega I over B to the power phi minus 1 over psi. Very different from the clean case. If you do the same thing in the clean system, this is B to the power 1 over delta. Delta is one of those critical exponents. And delta is 15. It's very different because it's a log and here's a power. It's a power that is almost zero. This is almost log, right? Because it's almost zero. So it's not that different quantitatively, but qualitatively it's very different. Yes, how is that? It's a constant, if I remember correctly. Yeah, I didn't mention that. Maybe someone here remembers. I think it's a constant. It does not diverge. Do you remember, André? I think it's a constant. Does not depend on T. But I may be wrong. But yeah, of the Pume. No, good. Thanks. No, I'm talking about the ferromagnetic easing. Maybe it's 1 over T. Maybe it's goes as No, it doesn't go to 0. It has to at least be a constant. Yeah. Google it. Constant or t minus 1. I'm not sure. Okay, goes to a constant. Whatever. Certainly is different from the dirty case. Correlation functions. So correlation function, how do you define it? So everything here, it's already said. In the slides, I put the integration constants, right? That epsilon not there. I just put when gamma goes to infinite is gamma square, which is what I put here. If you wish to do all the detailed math, you are very welcome to do that. Susceptibility. Yeah. Correlation function. So that's the definition of correlation function. And how do you compute it? When you do the decimation, suppose you have a cluster here, and this cluster, let's say, has some spins together, and there was some other that decimated here, and you are decimating another cluster here together, right? So in this, in the renormalized chain, this is a spin, and this is another spin, right? Maybe there was another one here. It doesn't matter much. So when this spin become correlated with this spin, that's the distance x that I put there. So this is site j, and this is site j plus x. Well, these two guys has to be decimated together. Because if they decimate together now in the j, then this becomes a new cluster, right? And they do that coherent tunneling. So the correlation is of order 1, because if these guys flip, these guys flip. So that's the coherent tunneling. So I have the probability, the correlation length is proportional to the probability that this guy and this guy become decimated together. So for this to happen, this cluster and this cluster has to survive at that length scale, which is proportional to x. It's a little bit x, half of x, or x plus something, but it scales with x. So this has to survive, and this has to survive. So this is proportional to the density square. But the density is 1 over x, this distance. So that's why you put x squared there. But why you put mu square? Because mu is the number of spins that are here. So this guy here at the large length scale, they are more or less at the same length scale because it's a little bit short, and so on. So you multiply by mu square. This is a very rough estimation, but you should compute the exponents correctly. And that gives that exponent 2 minus 2 psi phi. The typical correlation length is very different, because typically these two guys are not decimated together. Right? This guy here has nothing to do with that guy, and so on. You have to do some perturbation theory, and you're gonna see that typically two spins are not correlated. So you have a very weak correlation that falls exponentially fast when they become distant. So mean correlation length and typical correlation length, as we had here for the coupling constants, they are very different from each other. One is power law and one is exponential. All right, so much for the criticality. Let's go off criticality now. Any questions so far? Well, off criticality, we don't go to this universal fixed point anymore. We go to something different. P goes to what I'm calling P star over omega, omega over J, 1 minus P star, and the same thing for R. And when gamma goes to infinite or omega goes to 0, which value are those? Those are the following. P star equal to omega to 2 delta, when delta greater than 0, and 2 modulus delta, delta less than 0. So what are the, what's going on here? Delta greater than 0, remember, delta is log H minus log J. So delta greater than 0 means that the fields are greater than the couplings. And during the RG, this difference is amplified. Even if we start something like this, let's say that I have P and R that are very close to each other. If you do the RG, because they are very close to each other, let me draw even closer, be more dramatic. Because they are very close to each other, they will flow more or less like the same initially. So I will get R, and I will get some P. But once you build up the singularity, now R is much stronger than J for large values. And then you separate the energy scales. So P of J will be very singular. So this is P, and then you get something for R. So this is initial, intermediate, and the final. So in this from initial to intermediate regime, we do not have much of a difference between what we had at criticality, because both J's and H are being more or less like decimated together. H is slightly more decimated than the couplings. Then you don't see much of a difference because it's already width. So statistically, there's not much of a difference. Only later that this difference really amplified. We call this a crossover. I erased, right? but delta is PR over 2 log H minus log J. Delta positive paramagnetic side. Delta negative ferromagnetic side. Right? Who wins? And then you can see from that, right? If I go to delta greater than 0, what happens to P? P goes to 0, right? Very fast. So this is 1 minus an epsilon. Very singular. And what happens to R? R star goes to a constant. So it's 1 minus something, which is constant. So it's like that. So delta. Sorry. So I have to answer 2 questions now. The first question, the first thing actually, before I write the question, is realize something. We start initially with R and H that are close to each other. So you are barely off critical, right? If I shift a little bit, I'm critical. And then we discuss what's happened. Now I just step out of criticality. I have this. So initially you go as it was criticality. The system doesn't realize there is not much of a difference J and field. Later, these scales separate. And then we see the real off-critical behavior. That's one question that I want to answer. When these energy scales separate? That's the question number 2. When J's and H separate. The question number 1 is something that I want to tell you. When they separate, the J's are much, much weaker than the R's, the fields. So essentially, you have 3 spins again, because the couplings, forget it. The fields dominate. So what is the excitation energy now? The excitation energy you have to flip, and you have to pay the price of the field, right? So how much is that? This, do you have to pay a large energy to do that, or a small energy? You have to look at the smallest field. And the smallest field, well, there are plenty of them. So it's very easy to excite. So in this case here, there will be gapless excitations, even of criticality. This is very different from the clean case. In the clean case, if I plot the graph of the excitation gap, I get that. The excitation gap is modulus of delta, modulus of H minus J. Meaning that the system is only gapless at criticality. Away from criticality, you always have a gap. When here, delta, positive, H are very strong. So you have to pay the energy of the field to flip. The spins are aligned to the field. The excitation is to flip against it. You pay that energy. On the other way around, the spins, you're in the ferromagnetic phase, so everybody's up. So you want to make an excitation, you have to flip one spin, this space J, because the nearest neighbors are counter-aligned and is antiferromagnetic, so you also pay a gap. So that's the case here. But not here. I'm off critical and I don't have a gapped excitation. I have gapless excitations. And for the dirty system, what you have is something like this. This is called the Griffiths region, or Griffiths phase, if you wish. It's just another name. So this is the dirty. Yes, you can say your question. No, here is P and R. Well, it depends on, yeah, it depends on the value of this guy, right? Yeah, okay. It diverges much weaker. Okay. This number could be 1, right? Yeah, or not, yeah. Yeah, it's close to criticality, it will diverge. All right, thanks. So the first question is, what's the dynamical scaling of these off-critical excitations? And before going to this, I want to draw your attention to another important effect of random mass in phase transitions. Remember, we are dealing with random mass disorder, right? My disorder did not break locally the symmetry of up and down. So random mass disorder stabilize this Griffiths phase. Or induce. And the main point is they are gapless. Gapless Griffiths phase, off-critical Griffiths phase, you name it. So okay, so let's answer question number 1. Well, I just erased here, right? But dn p plus r and the omega. So the n is n p omega plus r omega, which is p star plus r star, the omega. And if you are above criticality, you get omega plus 2 delta. And omega going to 0, you get 2 delta. If you are below the critical point, P star is 2 delta modulus, and the omega goes to 0. So you get always 2 delta. So this n times 2 modulus delta d omega. Then you solve for it, and it's very simple. You get n goes to omega to 2 delta, which I defined the off-critical dynamical exponent 1 over z, as we did before here for the king case, because now this is L minus 1, and this is tau minus 1 to 1 over z, means that the tau goes as L to z, and the z is the off-critical dynamical exponent equal to 1 over 2 delta. When you go to the criticality, z goes to infinite, as we have seen before. Then you have exponential, the activity dynamics. So yes. It is observable. Yes, we're gonna see that in a minute, in a very simple way. I will give a new perspective of the physics of Griffith's phase in a couple of minutes. Sorry, what? Until when I have time? 12:30. So I have 20 minutes. Okay. Yes. This is when omega goes to 0, right? Because I'm always think at low energy. Right. Okay. So question number 2. When these J's and R's become different? Well, this is somewhat simple, because remember that R critical is the small r critical divided by omega, and omega over h to 1 minus r critical. And then I have just to compare this function with that function. So I have to see when this R star is different from R critical. When this difference becomes sizable. So R critical, remember it vanishes as 1 over gamma, and R off critical is 2 delta. Just there, let's say that we are in the paramagnetic side. So when I'm here and go here, these two exponents become very different, and then I get something. Then I get what I'm calling crossover, because now I make crossover when one over gamma is over order 2 delta. So if I were in the other side, I could use the same argument for P. I could put as a number here, delta, due to duality, right, between 8 and J. And then I get that gamma crossover delta equal 1, which gives me, of order 1. Crossover gives us omega crossover. Gamma crossover is 1 over delta. Omega crossover is omega I exponential of minus 1 over delta. So here is omega of other omega crossover. This is omega is smaller than omega crossover. And this is omega much smaller, sorry, bigger. Much smaller than omega crossover. Why this is interesting to understand these crossovers? Because I can do the following. This omega crossover, it gives me a crossover temperature as well. You can say that KBT is omega, and I get this curve here. This is T crossover, which is exponential of minus 1 over modulo delta. And as we have seen here, we have Griffith's phases surrounded. So I have, let's say, a Griffith's paramagnet. Here I have a conventional paramagnet. Here I have a Griffith's ferromagnet. And here's conventional ferromagnet, where the gap does the following, right? This is the gap. Let me draw in a different color. So if I do an experiment and I lower temperature here, like this, I'm setting some delta. Above T crossover, I'm running the RG as it was critical. So observables look critical. So this region above the dashed line is called quantum critical region. When I go below this dashed line, below the crossover temperature, then the observables get a different behavior, and now they look off critical. All right. This is important to interpret experiments. You see, when we are doing this RG near of criticality, when the energy scale separate, what happens to the RG? I just decimate coupling, fields. I remove them. I do not clump them together anymore. So if the spins develop some correlation by clumping them together, right? If I clump them together, I move this and this move together, so it build up other one correlation. But after this crossover, I will not clump any of them together because I only decimating fields. Just remove. But before this happen, I'm still clumping them together, so they still develop correlation up to that crossover scaling, which is crossover length scale. What is this? How can we compute this crossover length scale? It's very easy. It's already here. Because this crossover energy scale is the critical one, because before that, critical of critical doesn't matter much, doesn't have much of a difference. But before that, we saw what is the relation between length and energy scales. So this is energy, and I know how is the energy scale. So this gives us a crossover length scale, which is what? Psi crossover. I use the dynamical scaling that we had. Remember the dynamical scaling? The dynamic scaling, it's here, right? No, not there. It's somewhere. Second board from the right, bottom. Well, you can use that as well, but I was willing to use the critical one. It's easier. You can do that as well. But we get n goes to gamma minus 1 over psi, right? So we get L minus 1 goes to gamma to, so L goes to gamma 1 over psi. And so this crossover length is this guy here, which is gamma crossover length to 1 over psi. But gamma crossover length is 1 over delta. So if it is 1 over delta, I put 1 over delta. Delta to 1 over psi. So the off-critical correlation length, so the paramagnetic, Griffith's paramagnetic correlations are what? C of x will be exponentially small. We are off-critical, minus x over psi, where psi is the crossover length. Is when you come from here. Remember, we have a critical, here we have a critical-like correlations. It's a power law. Below here, you're going to have exponential. And these crossovers, where? At the crossover length, which diverges as 1 over delta to the power nu, with nu being 1 over psi, that is 2. Now I answer your question. Is now the crossover length, if I want to, the correlation length, and in both cases, due to duality, both sides, is 1 over delta to nu. And nu is 2. The nu clean is 1. It violates the Harris criterion. Now you have saturated the Harris criterion. All right. We can compute observables. Specific heat. What is this, the entropy? Oh, I erased the entropy. I will not do that here. I will put the entropy right here. And we have seen what's entropy, right? So it's proportional to the density of spins that are left. And this density of spin that are left, we computed here, right? Here. So this is omega to 1 over z. That is t as 1 over z. And z is the critical dynamical exponent 1 over 2 delta. So if you come here, doing this, entropy is like log. Remember, when you cross over here, you get a power law, t to 1 over z. So z is 1 over 2 delta. You come here, log, and then it will be a different z, because you are different distance from criticality. So all this region here has different exponents. And I would also say to you that everywhere here, we have different fixed points. Because the fixed point is tuned, I erased that, right? Is tuned by the value of z. So this is what we called line of fixed points. We have a line of off-critical fixed points surrounding a critical fixed point. Yes, that's a fact that is well known experimentally. Of course, I'm not raising too much. If I raise too much, then I get other physics. Yeah, because while this is high temperature here, right? Let's put your temperature here. This is high temperature. Yeah, the initial flow is like off critical. That's it, right? The gap is very small, right? A finite size gap is very small, as we've seen this activate dynamical scaling, right? Omega vanishes exponential of minus the square root of L, the finite size gap. That's this curve here. So when you are above it, you don't know if you are off critical or not, because everything is blurred yet. Okay, so now now that you have entropy, we can compute the specific heat, right? It's the same thing, and it will go as T as 1 over Z, because we divide by T but pick up a T again. So it's the same thing with a different prefactor of the entropy. There is something that we don't have in the critical point, the spontaneous magnetization. How is the exponential magnetization computed? Of course, it only appears for delta equals 0, which is the ferromagnetic side, right? In the paramagnetic side, there is no spontaneous magnetization for obvious reasons. So now I have to exchange. I will put R here and P here. So this is R, this is P. So this is R and this is P. When I cross over this energy scale, what I will do? I do not decimate fields anymore. Every spin that is there will gonna be clumped together, and will form a huge cluster that will percolate the entire lattice. So the magnetization is the sum of all these clusters, right? Because when you clump them together, the field will be very small. At the thermodynamic limit, you get a classical spin with a zero field. So it does not tunnel anymore. And it will be either up or down, spontaneously breaking. So in this case, how much is the magnetization? It's the total number of spins that were left over after the crossover. Because after the crossover, no one was removed anymore. So the magnetization will be proportional to the density at the crossover times the magnetic moment at the crossover. And we know where the crossover happened, here. So this is gamma cross 1 over psi, gamma cross 2 phi, and this gives us, if you use gamma cross there, this gives us minus delta to the power beta, with beta equal 1 over psi minus phi. Psi is 1/2, 1 over psi is 2, minus phi is the golden mean, 1 plus square root of phi divided by 2, and this is approximately 0.38. The beta clean is known. This is 1/8, which is 0.125. Almost 3 times bigger. Will I need this thing here? Finally, susceptibility. Susceptibility, you do the same thing, but then you have to compute this gamma, which of critical is not that anymore. Gamma of critical, it behaves as gamma for delta greater than 0, and this is the Griffiths paramagnet, and 1 over omega to the power 1 over z for delta less than 0. And if you can plug it together here, you have n of critical. You have to use that, and what you get in the end of the J when you do this calculation is that you get 1 over t, 1 minus 1 over z for delta greater than 0, and 1 over t, 1 plus 1 over z for delta less than 0. There are log corrections that I'm not putting here, but I want to tell you, of critical, the Griffiths paramagnet, you have a sub-Curie, and in the ferromagnet side, you have super Curie, which is greater than 1 here. So all of these looks like wave-hand arguments. It is wave-hand arguments, but all of these exponents were computed numerically, Monte Carlo, exact diagonalization in some case, and all they match perfectly. They are exact. All right. I would like to give you a different flavor of how to understand these Griffith singularities, but I ran out time. It's just 3 more pages. We can do that tomorrow. But tomorrow, I have a proposal. I don't have a proposition. I have a poll to make here. I could speak tomorrow of smeared phase transitions. Sometimes the effects of disorder are so strong that, well, the transition still exists, but it is not sharp anymore. It doesn't happen at a single critical point. It happens smoothly throughout a region. This is called smeared phase transitions. Usually they happen when your system is coupled to a BEF, or a thermal BEF, or a BEF oscillators. And they smear out the transition. The other thing that I could tell you is about dynamics. So you get a closed quantum system, do a sand and quench, and that depends on how is this sand and quench. You see the observables a long time, so you're doing real-time dynamics. And you're gonna see how these Griffith singularities affect the dynamics. So I have these two things to tell you, that I could tell you. And I'm open here for discussion. Which one do you want? So maybe I should put, I don't know, who votes in one, and then you come here to the blackboard and says, what do you want for tomorrow? Think over the, yeah, okay, if you want to vote now. Dynamical Griffith singularities or smear transitions? Okay, who goes to this one here? I hate counting. 1, 2, 3, 4. It looks like 18. So the other way around. And then I will know how many people we have in the Who did not vote? 1, 2, three did not vote, not voting. So how many people we have here? 20, 38. We have 38 here? Okay, that's a good number for the school. Or at least who survive at this up to this point. Yeah, okay. I don't count. Yeah, well, probably, I'm sure I miscount. I start counting English and then I switch to Portuguese and something. No, what do you mean? No, okay. I could do both, but then I have to use lots of slides. You see, okay, I will decide. Thanks. Oh, I didn't ask, is there questions about, maybe it's too late, right?